Alright, in this video we're going to do a numerical example to illustrate all of the concepts introduced until now on the first law of thermodynamics. Right, so this is everything that we have seen. We know that if you have a gas expansion, the work can be calculated like this. If you have a change in temperature in a system, the amount of energy transferred as heat can be calculated using the heat capacity. Then that's the first law. That is the first law under constant volume. This is the definition of enthalpy, and this is the equivalency between enthalpy, change in enthalpy, and the energy transfer as heat at constant pressure. Right, so we're going to apply all those concepts to the following problem. We simply have a gas in a cylinder with a movable piston. Right, so we have 2 moles of this gas, initially 2 atmospheres of pressure and a volume of 10 liters. And then what we're going to do is let that gas expand. Okay, at constant pressure. Notice that the pressure doesn't change, but the volume increases. So there will be a gas expansion at constant pressure. And then what will happen is that we're going to let that gas then undergo another change in which the pressure will drop, but the volume will stay the same. Right? So notice that that will be a constant pressure process. That is a constant volume process. Okay? Great. Other parameters of our problem are that this expansion takes place under a constant external pressure of 2 atmospheres. And then the heat capacities of this gas are, at constant volume, the heat capacity will be 3/2 R. And then at constant pressure, it will be the heat capacity at constant volume plus R. The goal is to calculate the energy transfer as heat, the energy transfer as work, change in internal energy, change in enthalpy in each one of the steps and in total. Alright, so then let's try to start here from the beginning. The first step, it looks like it's a gas expansion against a constant external pressure, and then we have to calculate Q, W, delta E, and delta H. Alright, so let's get started with work. Alright, notice that this is gas expansion against the constant external pressure, so then we know that the equation to use will be the external pressure times delta E, and then we actually have all of the numbers to do this, right? Notice that the external pressure will be 2.00 atm multiplied by the change in volume, which is 30 liters minus 10 liters will be 20 liters. Alright, so that is going to be equal to minus, and then after transforming this to joules, we'll have that this number is minus 4.05, 10 to the 3 joules. So about 4,000 joules of work. Right, we have already our first piece of data here. This is minus 4.05, 10 to the 3 joules. Alright, notice that this work is negative, and that makes sense because energy is leaving the system as it does work to push that piston out. That makes perfect sense. Alright, great, so that is work. What about heat here? Something very interesting about this process is that notice that the pressure is not changing, right? The pressure of the gas is not changing, yet the volume is increasing, right? Notice that the number of moles are not changing either. So the only way that this can happen, right, that you can actually push out that piston is if it's you're actually supplying some energy as heat, and the temperature of the gas must be increasing as well. Alright, so what actually happens here, even though it's not obvious from the data, is that there is a difference in temperature between this gas and that gas. This gas will be hotter. Okay, so that is actually going to mean that we're going to have a change in the amount of energy, or there's going to be a transfer of energy as heat, depending on the heat capacity and also depending on the change in temperature. Okay, so in order to be able to do this, notice that the root expression will be C delta T. Okay, we actually don't have a C, we have a molar heat capacity, so this is going to be equal to the number of moles that you have times the molar heat capacity times delta T. And notice that we're working under constant pressure, so here we have to use CPM delta T. Okay, and CPM will be simply CVM, which is 3/2 R, plus R, that is going to be 5/2 R. Alright, so we have the number of moles, that is simply just 2 moles. We have the heat capacity at constant pressure, 5/2 R, where R is just the gas constant, and we simply have to calculate here where the change in temperature is. Well, to do that, we simply have to calculate the initial and final temperatures and see what the difference is. Right, the initial temperature, for all these we can use PV is equal to nRT, and the initial temperature T sub A is simply going to be equal to P sub A, V sub A, over N, which is the same for everybody, and then R. All right, so that is 2 atmospheres, then 10 liters, 2 moles, and then 0.08206 atmosphere mole Kelvin, and that gives you a temperature of 122 Kelvin. Okay, that is your initial temperature. Your final temperature in this step will be T sub C. You can do exactly the same thing, P sub C, V sub C, and R. And then notice that what will happen is that, well, the pressure hasn't changed, but the volume has tripled, right? So your temperature must have tripled as well, right? So that is going to be 366 Kelvin. Okay, so we actually now have everything that we need in order to calculate the energy transference heat. Okay, we will have here 2 moles. The heat capacity at constant pressure will be 5/2 of the gas constant, and delta T will be the balance of these two numbers, which is 244 Kelvin. Notice that the number that you're going to get right here will be positive, and this is 1.01, 10 to the 4 joules. Okay, so yes, energy has been transferred as heat from the surroundings to the system, and that has resulted in an increase in the temperature of that gas. All right, so our second number right here will be 1.01, 10 to the 4 joules. All right, great. So we have work and heat for the first step, and then we still have to calculate delta E and delta H. Well, delta E is going to be, the change in internal energy is going to be trivial, because that is just going to be the balance of heat and work, and we have both numbers, so we simply have to add them up and then get what the delta E will be. Taking all significant figures, this is going to be minus 4.56, sorry, plus 4.56. That doesn't sound good. Let me actually make sure that I have these numbers right. 6.09, 10 to the 3, that's what it is. 6.09, 10 to the 3 joules has to be positive because heat is much larger than the work done. Okay, great. And then the last point here is to calculate what the change in enthalpy is for this process. Okay, now notice that we can use either one of these expressions and they will give you exactly the same number. But notice that the heat that we have calculated here is the heat at constant pressure, because we're working at constant pressure, right? So that heat is Q sub P. And notice that Q sub P is always equal to delta H. So we already have delta H directly, right? Notice that in this particular case, because we're working at constant pressure, the change in enthalpy will be exactly the same thing as the heat. All right, so those are delta E, delta HQ, and work for the first step. All right, now we have to do exactly the same thing for the second step and see how these things change. All right, great. So examining here the second step, C to B, we can clearly see that this is a process not at constant pressure, but at constant volume. All right, so then if we start here with work, notice that if this is at constant volume, then there's no change in volume, work has to be 0. That looks pretty easy. And it actually is. Notice that no work is done if that gas is not allowed to expand. Okay? Then we can look at heat. And here, what you actually have is that, notice that the volume is not changing, but the pressure is dropping. So that means that the gas must be cooling as well. Okay? The number of moles doesn't change. Right? So then if this is a heating or cooling process, then what we have is that the operational equation will be the heat capacity times delta T, but notice that we actually are always working with molar quantity, so this will be number of moles times the molar heat capacity times delta T. And then now we're working at constant volume, right? So what we actually have to do here is use CVM. Okay, and that value is given by the problem as 3/2 R. All right, so then the only thing that we have to do here is calculate what the change in temperature would be, right? We know that the initial temperature here, this T sub A was 122 Kelvin, T sub B was 366, and we just need to calculate what T sub C is. Again, we invoke here the ideal gas equation to find that T sub C will be equal to P sub C, V sub C, number of moles, and R. And when you do that, you will find that this number is going to be exactly half of that, because notice that we're halving the pressure, dividing the pressure by a factor of 2. All of the other parameters are constant, so that means that the temperature has to go down by a factor of 2 as well. Okay, so that temperature is going to be 183 Kelvin. Okay, so with this T sub c, then we're ready to actually solve here. Then what you will have is the number of moles, which is 2, multiplied by 3/2 r. Delta T will be equal to 183 minus 366. Right, so that's going to give you a negative value for that energy transfer as heat. And that value for the energy transfer as heat is minus 4.56 10 to the 3 joules. Okay? It makes sense that this number is negative because the system is cooling, which means that energy is leaving the system as heat. Okay, and that's why it's a negative number. Okay, so here we have that this is equal to 4.56 10 to the 3. All right, very good. Those are joules. So we just have to calculate here delta E and delta H. And then for delta E, we can use either one of these recipes. Well, work is 0, so notice that they're actually exactly the same. So change in energy is simply going to be equal to the heat. So this is equal to minus 4.56 10 to the 3 joules. And then the last remaining property to calculate here is the change in enthalpy. All right, so let's see what do we do for that change in enthalpy. All right, so for the change in enthalpy, we have these two numbers, or these two ways to calculate it. We actually already have delta E, so it looks that this might be actually really simple to do, right? Delta H is going to be equal to delta E plus delta nRT. Again, we already have that number. It's minus 4.56 10 to the 3 joules. And then we just have to evaluate what this is. Well, notice that something interesting here is that the number of moles doesn't change. You have 2 moles to start with, 2 moles to finish with. R is a constant, so there's actually not going to be any changes to these 2 numbers right here, which means that this is the same as nR delta T. Yes? And this delta T we already know. Notice that that is going to be 183 Kelvin minus 366 Kelvin. Right, so we actually have everything. Delta E we already know as well, that is minus 4.56 10 to the 3 joules. The number of moles is 2, and R, here you have to work in joules, so that will be 8.314 joules per mole Kelvin. So then the calculation now is straightforward. We have everything that we need, and then we can conclude that this is equal to minus 7.61 10 to the 3 joules. Okay, minus 7.61 10 to the 3 joules. All right, so now we have the change in raw energy, change in enthalpy, work and heat for each one of the 2 individual steps. And then the idea here is that the total will simply be the sum of the change in raw energy, change in enthalpy, heat and work for each one of the individual steps. We're not going to do those numbers, but again, it will just be the straight addition of the individual steps. All right, so in this video we have illustrated essential concepts in the first law of thermodynamics for process in a gas. Okay, the process was complicated in that you actually had processes, sub-process at constant pressure, another one at constant volume. The temperatures were changing as well, and that has allowed us to illustrate all of the concepts that we have introduced until now.